The thing that I like about programming is I actually think it's very expressive. It is a creative activity, it's a craft. I mean, they're called programming languages, but it is a language and you can write code that is, beautiful, elegant, and all of that. It's a personal aesthetic, so I can write code that I think is beautiful and elegant. Other people may not think that. But I like the challenge of trying to express an idea, to get a machine, a computer or a robot to do something, but to do it in a way that's elegant, clear, understandable. They're the same constraints you have when you're writing prose or writing a textbook. And so I think it's that expressiveness that I find most seductive about programming. So I was born in East Melbourne in 1959, and grew up in a house in suburban Melbourne. Nothing particularly remarkable. I guess I grew up with reading a lot. I guess that's been a constant thread through my whole life. I was interested in cameras. At one point, my dad was a photographer, and he gave me sort of cast-off cameras which I could play with. I'm not sure if he gave me film, but I've definite memories of cameras. So my dad was always interested in natural history, particularly birds. So he'd been an avid bird watcher his whole life, and moved from that, I guess, into documentary filmmaking with a bunch of mates. It's a self-financed weekend thing, and then he got a paying job with CSIRO making documentary films.
We're now proposing to shift the telescope. Has anyone any objection to the telescope being shifted? Aerial cabin, anyone in the aerial cabin?
I remember he talked a lot about how some of the scientists that he was filming at CSIRO were using, today we call it transdisciplinary research. So the people are doing computers, and they would work with somebody who was doing pastures or oceans or atmospheres, and they were sort of applying computer technology, which was nascent at that point, to all these new growing areas. And so that's probably something that stuck with me. And these days it has a name: transdisciplinary, interdisciplinary research. It's where interesting stuff happens when you bring two fields together. Each has got something to add, and in aggregate you can do more than either of you could do before. I think by the time I got to high school, I was very definitely in the sort of science, maths track, and moved to Central Victoria in 1970. So I went to a country high school, and so in the Form 6, Year 12, there was about 35 of us, six boys and the rest were women, right? And that's was kind of extraordinary. I was very shy, so it was just terrifying, but but it meant that the class size was small. So for my maths and physics and chemistry classes, there were just 4 of us, which was extraordinary. We had fabulous teachers, a really small class size. The school was really well equipped. So that, I think, was very influential to me. So I knew years and years before I had to make a choice about which university I went to or what course I wanted to study. I think I just knew I wanted to do engineering. There was never any doubt about that. I built a lot of electronics during my teenage years. So my bedroom was kind of a workshop, soldering irons and lots of electronic components. But mostly it was radios. Radios was the sort of the electronics tech of the time. Computers existed, but they were not really accessible at a personal level. But I started programming when I was still at high school. At my school, I had a teacher, and he was doing some further study at Bendigo, which was the big smoke, 20, 30 kilometres away from Castlemaine. So once a week, he would go up to Bendigo to do some courses. And I don't know how he managed to wangle this, but he got me the opportunity to program. So I'd write my Fortran code on what's called a coding sheet. It's like gridded paper. I'd write my code on that. He would take it to Bendigo. Some people would punch it onto cards, and then the cards would be put into the computer, and the computer would run them. This big stack of fanfold paper would come back. So, once a week. And so fanfold paper would come back and say, oh yeah, the program didn't work, there was an error here. You'd fix it up, you'd make some notes on a coding sheet, it would go back, they'd change the cards, run it again. So you had to wait a week, right, to get a turnaround of the code. But if that's all you got, you can make it work. And so I wrote programs to do all sorts of things, print biorhythm charts and stuff like that. It was fun. I wanted to do electrical engineering. I knew what I wanted to do. Engineering at Melbourne at the time, you have to do a common first year. I didn't want a common first year. I knew what I wanted to do, right? So having to learn about concrete and magnetic materials and things like that, that wasn't very interesting to me. But anyway, had to do that. But yeah, I had no exit plan for university, what I would do at the end. So that was just really a complete accident. Well, I got interested in control systems, and there's a professor at the university, a guy called John Anderson, and he had a control systems lab. In the lab there was this gorgeous computer. It's called a mini computer, and so it's as big as 3 refrigerators, right? But it had some interactive terminals, and it had 2 hard drives. Each hard drive was as big as a washing machine, right? It was 28 megabytes. Yep, that's the tech. But at the time, it was gorgeous, and so I used to hang out in the lab a lot and play around the computer. I wrote a really simple Trojan horse. It's not particularly clever. But what it did was spoof the professor into typing his password into a program, which was my program, not the login program. So I got his password. And once I had his password, then I had admin rights to the computer, and then I could find the passwords for everybody who used the computer. So I was a bit cheeky. So anyway, I printed out the list of everybody's passwords. So the security on the system was completely rubbish. So it was not a particularly difficult trick to do. Anyway, so I printed it all out and I stuck it under his door. He figured out who had done that, and he didn't chew me out, he offered me a job. So that was the exit plan then for undergraduate sorted. So I had a job as a research assistant in the same school, in the electrical engineering school. And so first year was complete bliss, because then I was paid then just to do stuff with computers. So I spent a lot of time playing with that, writing code applications for that to support the professor's research. Then he won a big grant. After I'd been doing this for a year, he won a big grant. And what academics often do when they get a big grant is they buy themselves out of teaching. It meant he didn't have to do his teaching anymore, so he paid me to do his teaching. My position at Melbourne Uni was coming to an end, and so I was interested in robotics. And then just magically there was this advertisement in the newspaper, CSIRO were looking for someone to do robotics. And they had a lab just down the road from Melbourne Uni, so it was very fortuitous. So I interviewed, I got the job, and went to work for CSIRO at the beginning of 1984. And so my first day of work, I rock up there all wide-eyed, bushy-tailed, and the guy who was my boss said he's leaving. He'd resigned, got another job somewhere else. And so that was interesting. So he'd had the foresight to buy a lot of gear before he left. So this was a relatively new CSIRO division that had been created with a lab in Fitzroy in inner city Melbourne, and it was division of manufacturing technology. And so this was a robotics group that had been established in Fitzroy. And so my boss left and I was there with a lot of equipment, and we had a few other people came in at a senior level. And the first project that I worked on there was what's called, back in the day, a flexible manufacturing cell. You've got a bunch of machines, a few robots and conveyor belts and vision systems and stuff, and we wanted to configure them so it would do something useful to show people in industry who weren't using robots what robots could really do, because there weren't too many use cases in Australia at that point. And so, it was to build a demonstration what they could do. So we wrote code for all the different robots and communication systems so they could talk with each other. And we had a German visitor at that time, Hartmut, and he kind of designed the overall concept, and I was put to work to design some of the robot code. And that was a great experience. And we ended up with a system, your user could go up to it and they could say what kind of little gearbox that they would want manufactured, and it would manufacture one of 4 different types of gearboxes. Type the gearbox you want and the robots would go to work, and milling machines would cut metal, and parts would move along conveyor belts and be inspected, and gears would be inserted and meshed. It was pretty cool. So that was a kind of first big multi-person project I think I'd ever worked on. But in the same lab there was another group of people who were working on a vision system, computer vision system, and that wasn't really my project. But CSIRO in those days was pretty free form, and so you could, if you go and talk to those people and hang out with them, and you could become part of their project too. So it was a wonderful freedom that existed in that lab at that time, and that's kudos to the people who led the lab at that time, that they gave us that kind of freedom. So the Vision System project was about how do you take an image from a camera and figure out what are the objects within the scene. To do this with all in hardware was pretty amazing. So I kind of bolted myself onto that project as well. So I had a foot in 2 camps. Right? I had a foot in one camp which was looking at robotics, and foot in this camp, people looking at vision. So while I was doing that vision stuff, another person had come to CSIRO, a guy called Malcolm Good, and he had been at Melbourne Uni in mechanical engineering, and then he'd gone overseas on a sabbatical to the US to General Electric research labs, where he'd been doing a lot of work on robotics, and particularly how do you get a robot to have a sense of force perception. So there are lots of jobs that robots need to do where they need to understand the forces that they exert on the world. So Malcolm had come back from the US, he'd been working on this problem at GE, and so we started working on that in the lab. So trying to equip a robot with the ability to sense forces that it was exerting on the world, and use those forces that were sensed to control, change, modify the motion of the robot. And the particular problem we looked at was called deburring. So in a lot of operations in manufacturing, particularly in casting, an object that's cast has got all this ragged edge on it. And a human grabs a deburring tool and they whiz it along and cut off the flashing, the rough edges. And that's a job that requires a sense of force. If you push too hard, you're going to gouge into the object, which is not helpful. If you go too lightly, you're going to leave some rough edges behind. So the idea how humans have got that skill, and we know it's done by force sensation through their hands and their fingers. How can we imbue a robot with that same capability? I was inspired in doing this with some robot control software which had come from a lab in the United States, the University of Pennsylvania. So some of my code was inspired by that, but different to that. I thought it was more elegant, improved on the version that I'd received from that university. So I was working on controlling robots, and I was working on this high-speed vision stuff. I then was fortunate enough to win a fellowship from CSIRO that let me study overseas. 1988, set off for University of Pennsylvania, which is in Philadelphia, with my wife and 9-month-old baby. We lived in inner city Philadelphia on 47th Street. It was particularly hard for Philippa with the baby, and I'd go off to the lab every day. And I had great fun. It was a great lab. Philippa was essentially stuck in the apartment with a little baby, and so we go, did a lot of travel around the US. I was really interested to try and bring together these two things that I've been doing. One was this robot control that could make use of this force information that came from a sensor attached to the robot, and this high-speed vision stuff that I've been doing. And so I had this idea in my head that I could put these two things together so I could make a robot that could respond to visual information really quickly. This idea of using camera information to control a robot, it's a technique called visual servoing, which is an ugly word, but it's what it's called, has been then sort of a thread through the rest of my professional life. When I was in the lab in Philadelphia, I was the only person there who didn't have a PhD or wasn't working towards a PhD. So I was the odd one out in the lab there. And the CSIRO promotion system had a glass ceiling for people who didn't have a PhD. So coming back and figuring I really wanted to do research, I'm going to bump into the glass ceiling pretty soon, I should sign up and do a PhD. And I was highly motivated coming back from the stint working in a top research lab with lots of other people working on PhDs. I thought, yeah, I could do this thing. I was doing my PhD part-time and working for CSIRO, and they were very generous about that. So, they gave me sort of half my time I could spend working on my PhD, half the time I could spend working on projects at CSIRO. And when I started, the two things were almost completely aligned. Over the 3 years, they separated, and that made things a bit awkward and stressful, to be honest. My boss at CSIRO said, would you be interested in going to Brisbane? And so quite comfortable, content in Melbourne, but there was an opportunity in Brisbane because CSIRO had become involved with a research centre which has been established in Brisbane, which was looking at mining technology and equipment. And the idea was automation has made big improvements, productivity gains, safety gains, and so on in manufacturing industry. But it was non-existent in the mining industry. The mining industry is a huge industry in Australia. So could some of the ideas from robotics and computer vision be applied into the mining industry to improve some of the challenges that they faced? So in that period, after I moved to Brisbane, hired a guy called Jon Roberts, and worked with Jon for a very long time, since 1995, and he's now a QT as well. So Jon is one of the most organised people that I know, far more organised than I am, and incredibly disciplined.
Our companies here can work with us and develop kind of proof of concept systems before they actually decide what to commercialise. And over the next few months, this area will generally fill up, and we'll kind of grow this entire area into a robotics company precinct. I guess the first real memories I have was when I was 7 and saw Star Wars. So I was one of those people that lined up with my parents, because I would have been like 7.5 or something like that when Star Wars came out. And that kind of set me on my track of, getting into tech and space and stuff. So I became obsessed with space at that point. So I went to the library and got all the space books out of the library, and that was my obsession with space. So I decided I'd be an astronaut, as you do when you're 7. So my whole kind of rest of my childhood was kind of building up to figuring out how to be an astronaut. So about halfway through my degree of aeronautics and astronautics, I had this option to sort of take a slight, tangent and go down a different path. And I took that option, which was called aerospace systems engineering. And that's where we focus more on computing and all the electronics and software and programming associated with aerospace and space. So that's how I kind of finished off my degree. At the same time, I also just tested sort of, my courage out. Could I be an astronaut? So I took up parachuting, rock climbing, did a few flying lessons, all that sort of stuff, just to make sure I wasn't going to be too scared. Did some bungee jumping, and that was all good. I mean, it was scary, but I could throw myself out of a plane. That was fine. And then I, hunted down a PhD. And then I remember a very amazing day where I had an appointment to ring my supervisor to see what PhDs were on offer. And before that, I had about 3 hours to kill, and I went to see a movie, Terminator 2. And that movie, as most people will know, is about a robot, and there was a lot of robot kind of vision stuff. So there was a lot of that. You would see through the eyes of the Terminator, right? And you'd see all this kind of cool stuff. So I got out of the cinema, rang up my supervisor, and he said, okay, we've got 3 PhDs on offer. You could do one in jet engines, I think it was, one in some sort of aerodynamics thing, and one in robot vision systems. And I'm like, well, that's pretty easy. I'll just do the robot vision systems one. My particular bit was tracking other cars. So there was a camera in the front of the car, and as other cars overtook, I had to figure out how to track all of these other cars automatically and write the software, to take those images and then track these other cars. And that's kind of what my PhD was. And working out how to do that fast. Because back then, of course, computers were very slow, and we had to use these, kind of small supercomputers to try at least prove the concept, hoping that in the future someone would invent much faster computers that could do it. So after the PhD, we came back in the beginning of 1995. At the time, I didn't, again, it was hard because the internet was only in its infancy, so it was hard to find a job ahead of time. So I came with a couple of magazines of, I think it mentioned, a few universities and things like that. And when I arrived, I then started making contact with people. And one of the people I made contact with was Peter Corke, who had just moved to Brisbane himself from Melbourne, and he worked at CSIRO. I went, had a coffee with Peter out at the CSIRO facility, and with another gentleman called Graham Winstanley, who had worked at CSIRO for about a year. He'd previously come from QUT, where I now actually work. And anyway, we got talking, and it turned out I had some unique skills in running this particular type of computer system, which they had just purchased at CSIRO to do a whole lot of this same vision stuff, and I just happened to be one of the only people that knew how to run this stuff. So it was kind of a nice coincidence, and I started working there a few months later.
We worked on a number of really interesting projects in that period at CSIRO. We worked on automating dragline excavators. Draglines are massive machines. They're like cranes. They weigh 3,000-4,000 tons, pick up 100 tons of dirt at a time from a pit and put it onto a spoil pile to uncover coal. And they're manually operated machines. Productivity is an issue. So we figured, well, it's a machine. It's just like a robot, but bigger. How hard could it be to turn that machine into a robot?
Peter and Graham had been working on that for the year before I arrived. And then when I arrived, we started doing some kind of serious field work and actually trying this stuff for real. And we started on a scale model, which was based out in Brisbane, sort of near Ipswich. It was like a 10th scale model dragline. We implemented all this vision stuff that I knew about from my PhD days. And we discovered it was actually quite a hard problem. We put a camera on the top of this dragline looking down at this bucket, which was full of dirt. And of course the background is dirt. And anyway, it turns out that looking for a bucket of dirt in a background of dirt is hard. So, after a while, we kind of gave up on using the camera system, and we bought some lasers. And we'd figured out that because we've got these ropes hanging down, lifting this bucket, if we put the laser kind of looking out horizontally, we would see these 2 ropes swinging past. And that was kind of the secret of the dragline system, to actually figure out where this bucket was. So the heart of the problem was how you control this very heavy bucket, which may be 100 tons, and it's kind of swinging around because the dragline kind of picks up from one spot and rotates on the spot and dumps the dirt somewhere else. So it's a pendulum, basically. And Peter was the control expert in how you control a big pendulum like that. And it was my job to actually figure out how to measure where the ropes were on that pendulum. And Graham was managing the sort of the whole project behind the scenes.
We also worked on an underground driving project. So there are these machines called load haul dump units. They're like front-end loaders, fairly squat, and they drive through underground mine tunnels with a scoop full of ore. So they pick it up from where the ore's been brought down, and they drop it into a crusher or something like that.
You could get uncontrolled ceiling collapses in the mine. So the mining industry, of course, has always been focused on safety. And there was a desire to remove the operators from potential harm's way. And up until that point, that had been done by radio control. So some people had experimented with taking the operators off the trucks and putting them in a sort of a cabin, still underground, and radio controlling the trucks. And that had been demonstrated quite well. But the problem with that was apparently they lost productivity. Because if you are radio controlling something, you kind of lose all that seat of the pants feel. So it turned out that they went a bit slower than you would if you were actually in the seat. So the natural next step was can you kind of semi-automate this and turn them into driverless trucks, where when they're going down the tunnels, these lasers and the control system actually doing the steering, and then when it gets to the hard bit, which is digging out the dirt, then the operator comes back and takes over with the remote control and kind of does the digging, and then presses a button, and then the truck automatically zooms off as fast as it can, and that's what the project was all about.
Around the same time that I moved to Brisbane, a guy called Hugh Wyeth came to the University of Sydney from Oxford, and Hugh's got a big background in robot navigation, and he was particularly interested in applying that to what's called field robotics. So these are robots that move outdoors. And he had some background certainly in automating big machines at container ports, and he was very interested in automating mines as well. So some of the projects that we did were in conjunction with the Centre for Field Robotics that Hugh had established at the University of Sydney. So when Hugh came out, he brought some PhD students with him. One of those PhD students, Paul Newman, someone that I've gotten to know quite well over time. Paul worked did his PhD at Sydney, then he went back via MIT back to Oxford, where he now leads a very big robotics lab in his own right, and has a spin-off company called Oxbotica.
And I'm going to hang the technology that we're building off that single moniker. How can we do everything efficiently to build universal autonomy? And I'll walk you through what the universal autonomy mantra means.
I was contacted pretty much out of the blue by a guy called Greg Hager. And Greg had been at the lab at the University of Pennsylvania. He'd finished his PhD there, and we overlapped by hardly any time at all. So he was leaving as I was arriving, but his interest was in vision-based control also. So he contacted me out of the blue in '96. He was interested in writing a paper with another colleague, a guy called Seth Hutchinson. I'd never met Seth. We were going to write the definitive tutorial on this topic called Visual Servoing. So it was a special edition of a journal. We were going to write the lead article, which is everything you need to know about visual servoing. And so this was done completely remotely and electronically. So they'd sort of flick the files to me, and I'd do some work on them and flick it back to them. So the files just went round and round the world. It was quite an intense period of time. I think Greg had a baby born during that particular project, and it was intense. But the article was published in '96, so maybe we were working on it early '96, '95. Turned out to be enormously successful. That was my most highly cited paper ever by a long way. So it just hit the spot at the time, and the notation that we laid out, the way you think about the problem, the taxonomy of the problem space, that still stands. In 1999, we went back to the US, and this time we went to a university town in the middle of the US called Urbana-Champaign, and the University of Illinois has a campus there. It's a very excellent engineering school, and had two colleagues there. Seth Hutchinson, who had worked with on the Visual Servoing paper, another guy called Mark Spong. Now, Mark is a serious robot control and dynamics person, colleague of Malcolm Good, my PhD supervisor. And I went there to learn something different, particularly to get back into this area of control, which had been my old interest, but I got diverted into robotics and vision, and I thought I'd go and learn a lot of really cool control stuff from Mark Spong. I did. I also spent a lot of time talking with Seth, and we worked on some interesting problems in visual servoing. It's a field, there's lots of interesting questions still to be addressed and thought about, and so that gave me the opportunity to do that, and we wrote a paper, again was quite successful on a particular very narrow problem in visual servoing. So we understood it and came up with some ways to get around it. For the family, it was an interesting experience. We arrived just before the US summer holidays. So my girls both went to school in the US for a few weeks. People there thought that their accents were cool, but their time in school was quite short. So we homeschooled them, and we did quite a bit of travel around the US. The group that I was leading got bigger and bigger, and so in the decade of my 40s, I'm starting to move into research leadership, research management, and being less hands-on. It's challenging initially, but it's an important role. And certainly as a younger researcher, I'd benefited from great leadership and great management who gave me the freedom to do things and work in a wonderful, exciting environment without too many internal boundaries. So, as you become a research leader, they're the sorts of things that you'd like to set up, create an environment where people who are working for you, they've got those same freedoms, where they can flourish. That's basically your job. Create an environment where other people can flourish.
I think I was probably in about grade 7 when my brother received a 75-in-1 electronics kit, which he didn't use at all. And I started playing with it and got it to do things and started making electronics work. And then, so for Christmas, I got the 150-in-1 electronics kit and made that work, and then started hooking them together, and then I hooked that up to my Lego, and that really started to get my interest going in electronics at that time. I went into high school, I was already building circuit boards, I built a metal detector, I was making all kinds of devices, making my own musical instruments. It was a lot of fun. Peter was he was up there, he was definitely international superstar of robotics, and I was very much the just finding my way kind of young fella. But Peter, on the other hand, was definitely the man on the move, and the work that he was doing out at CSIRO was certainly legendary. Alex Zielinski, always a mover and a shaker. And back in '99, he and one of Australia's senior roboticists, fantastic roboticist. He was in ANU at the time, doing great things down there, but he really wanted to have an Australian conference on robotics and automation, and he was president of the Australian Robotics Association at that time. So he organised a lunch at the University of Queensland Staff Club with Jon Roberts and myself, sat us down and said, boys, I'd like you to run an Australian conference on robotics and automation. I think you two, who didn't know each other at all at that stage at all, would be a perfect pairing to get together and run a wonderful conference up here in Queensland.
There had been a few conferences before, but not a sort of a regular repeating conference, and he suggested to Gordon and I, as junior-ish researchers, that it would be good if we started this conference up. So that's what we did. So we met up and started this conference, and it's run every single year since that time. And we invited people from all over Australia, got a few international speakers, And it's just become a standard part of our calendar where at least once a year, everyone in the region gets together, and we expanded it to include New Zealand. So it's now known as the Australasian Conference in Robotics and Automation.
While I'd been in the US, Jon Roberts had been looking after the group, so I came back to find that we had a project in autonomous helicopters.
So back in 1999, we bought our first radio-controlled helicopter. So just after the underground truck project finished, we started trialling flying these radio-controlled helicopters, and I ended up accidentally being the test pilot for those first experiments. So I had to teach myself to fly radio-controlled helicopters, all at CSIRO on work time. So I mean, it wasn't a bad gig. So we would spend quite a few months every day just learning the ropes of flying these helicopters and kind of installing vision systems on there and computer systems, and generally trying to work out how you can get one of these helicopters, which up until that time had been radio controlled, to fly by themselves.
While I was in the US doing my PhD in robotics, working on autonomous helicopters back then, my PhD supervisor had done some joint research with Peter early on, so they knew each other, and Peter came out to the US and we did a joint research project where got to know Peter, and then around 2004 basically invited me to come out to the CSIRO lab and spend a couple of months working with them out here. So I got to know Peter and Jon and sort of the core team that were part of the robotics group back then. I really enjoyed my time with them. And then as I was finishing up my PhD end of 2005, they were hiring to sort of grow their robotics group into the drone space. So decided to apply for that, and that's how I ended up here. There were no off-the-shelf drones really that you could go and purchase. So what we were using was an adapted radio-controlled helicopter. So a petrol-powered machine, almost 2-meter rotor diameter. So a big machine that could lift, I think, almost 10 kilograms. There were no off-the-shelf autopilots that you could just buy and use. No electric multi-rotor drones. So we built the flight control system from the ground up. So yeah. Much harder than it is today, where you can just go and buy a DJI off the shelf.
So the UAV Challenge was a flying robot competition we created in 2005. And we came up with the idea to see if we could push the world into kind of accelerating the development of UAVs. And it was an idea with my colleagues, Professor Rod Walker and George Curran. So George Curran was one of my colleagues at CSIRO, and Professor Rod Walker was an academic at QUT at the time, and I was at CSIRO as well. We kind of proposed this competition at the end of 2005 to our bosses at the time, and then we spent the next year and a half developing the competition, getting sponsorship. The Queensland government were extremely supportive. Boeing Australia were extremely supportive and helped run this event. And then we actually launched the event in 2007. And we've run a UAV Challenge event every year since then. Back then, the competition was all about search and rescue. So we invented this character called Outback Joe, who was this mythical character who would always get lost on a bushwalk. And the scenario was teams had to develop some sort of UAV to go and automatically find Outback Joe and drop a water bottle to him and then fly back. And we kind of didn't realize just how challenging that would be. And it took a very long time. It was 2014 before a team actually fully completed the mission. So the first years of the UAV Challenge were kind of disappointing in a sense that teams would turn up and, the first few years their aircraft didn't even leave the airport. They would crash before they even got to the boundary, or we simply wouldn't allow them to continue because we had lots of safety checks, and we really wanted to be confident that they could fly and find Outback Joe. UAV challenge was hard because at the time the kind of the autopilots for these kind of small aircraft weren't that well developed. There had been, of course, autopilots used by big aviation companies, but on the small scale they really weren't readily available. So most teams would have to develop their own systems. And we had many teams that would turn up with very beautiful aircraft. We would also always make sure we had a beautiful team photo of them with their UAV just before. Some of them were very busy and would say, can't we do the photo later? Well, I know, probably need to do it before because you probably won't have your aircraft in a few hours' time. And that was, in the early years, that was the story. They would take off and crash and burn, and literally burn. I mean, there were a few fires and aircraft burning.
So during the late 90s and the early part of the 2000s, I was starting to look at lots of structures made out of artificial neurons. In other words, devices that computed in a very rough approximation of what the neurons inside our brains do. And at that time, I met up with Professor Janet Wiles, also at the University of Queensland, who's a cognitive scientist. And she said, you're trying to get robots that navigate, and one of the key brain structures that helps rats to navigate is the hippocampus. And in fact, the hippocampus has got some of the best computational models of any part of the brain. Have you ever thought about using a computational model of a hippocampus to make your robot work? I applied for my first research council funding, and I was very lucky to get it. They gave me just 1 year's funding just to explore this idea a little bit further. And that was enough for me to recruit a student called Michael Milford to start looking at, well, let's really try and make some robots that understand the world, not just react to the world, but actually retain an understanding of the layout of the world, because that's what rats do. But let's do it on a completely different premise. Let's do it on the premise that we're retaining the sequence of images that helps us recall how to get to a place, rather than building some kind of geometric map. And that's how the notion of RAT-SLAM was born. So SLAM is the problem of simultaneous localization and mapping, SLAM, SLAM. RAT-SLAM took all that geometric optimization and threw it away and said, well, a lot of the time you can know where you are just by looking at something. I can show you some key images, and you'll know exactly where you are, right? So, if you saw a key image, like the one behind me, you'd know you're in my kitchen, right? And so can't we use these visual place representations to get us from one place to another? Because that seems to be what the rats do. We started out doing this work with some quite precise, what we thought were reasonably precise models of hippocampus, then started to learn more and more about what's actually involved inside a brain. And that work went off on one angle, and on the other side we said, well, we're getting some amazing engineering results. And so we took those on a different journey again. And those were kind of the two paths that I travelled over the next decade or so. The challenge then that Michael, who was my postdoc then at this stage, undertook was to strap a laptop to the roof of his car and drive around the suburb of St Lucia, recording the video as it came into the camera on his laptop. And so we drove this path through every street in St Lucia, looping around, going backwards, just recording the video stream. Then we played that video stream through the RAT-SLAM algorithm. So the RAT-SLAM algorithm taking this sequence of images and places that it recognises. And over the 2 hours or so of driving around this suburb, the sun's changing, clouds are going up and down, shadows, there's traffic, there's different people. Would the algorithm be able to recognise that it got back to the same place, even though it looked different in subtle ways, based on the fact that there were sequences of images that allowed you to pull the street together? This was the breakthrough result. When we had this result and the beautiful video that Michael had, not to mention all the huge amounts of legwork that nearly killed him to get that done, this was the video that people saw and went, actually, there's something in this. There really is something in this. And I think that was the point that the whole field of visual place recognition really started to take off.
I think part of the motivation for diversifying was that we're working in a sector that has booms and busts, so we needed to have a broader portfolio. The other thing I think is actually having worked at mine sites and looking at what open cut mining does to the environment. I mean, it is like being on the moon. It is so barren. And I think this is where we thought we need to sort of balance the karma and put something back. So we started getting interested in what could robots do for environmental monitoring.
A student at QUT developed a first submarine, which was known as COD. It was known as COD purely because when it was manufactured, it actually said cash on delivery. They had this COD symbol stuck on the side. Again, we tested it in the creek out at CSIRO and at one of our technicians' swimming pools. He lived nearby, so we went and tested that out. So we started to explore this, UAVs and submarines and generally kind of build those projects up. And it was about that time that Matthew Dunbabin arrived at CSIRO, and he very much took on the submarine work.
Matt is incredibly self-sufficient. Matt just needs Matt, and he can do almost anything. So you give him a task and he'll build the hardware and write the software and do the field testing, the whole kit and caboodle. I think he's most happy working by himself.
So I was doing my PhD here at QUT. I started as a mature age student doing my PhD, and an opportunity arose to do mining robotics out at CSIRO through Peter Corke's team. And I was successful in getting that. So even before I finished my PhD, I was actually brought into the group over there. And that was a great little group at the time because we were doing very advanced mining robotics. I've always had a passion for the environment, but I just saw a couple of concerning things coming up. One was around the Great Barrier Reef and the plight of crown of thorn starfish that was starting to eat large amounts of coral. And I put it to Peter Corke that I wanted to actually develop a robot that could identify and inject these starfish. So once we decided that we're going to work in the marine domain, we needed a robot that was vision capable, which there was nothing out there at the time. We actually even had to build our own cameras at that time. But there was also no platform, so we actually developed what we called the Starbug. It was a robotic system, the first of its type that was vision only to do marine observations. This is RangerBot, and this is what we call an autonomous underwater vehicle. Now, what that means is once we set it off on its mission, it drives itself, it moves around by itself. Now, what is very unique about this vehicle is it's vision only. So we have stereo cameras at the forward looking, and they provide obstacle avoidance and some of the science data. And we also have stereo cameras downward, and they allow us to estimate our position, our altitude above the seabed, but also collect other data, for example, the crown of thorn starfish and types, things like that. We have a payload rack here, we can attach different payloads. But the other interesting thing about this is it has 6 degrees of freedom of motion. So we have 6 thrusters in a very unique configuration. And that allows us to go up, down, left, right, around in every direction. And that's important because in a coral reef environment, we actually want to be able to avoid hitting anything. We absolutely do not want to hit any coral. And it might mean that we have to stop, go backwards and raise and lower ourselves. So this robot has the ability to do that. On board, it has 2 computers, one simply for navigation, but one dedicated to the vision system. That's how important vision is on this system. It has to have its own computer. And on the back, we have removable battery pods. So we can extend the life. So normally this has about 6 hours endurance, but we can easily swap out batteries to give it full operational day.
I had for a longest time this idea of writing a book about robotics, different textbook. So yeah, it's not a book for kids. It is a textbook aimed at university level, and it'd been kind of bubbling around in my head for a longest time. I thought it's an opportunity to actually do it. I'd made an attempt many years before to do that and failed. So I mean, to take out some time, go somewhere nice, write a book. But this was the year that I turned 50. And at that point, I'd worked for CSIRO for 25 years. So that's half my life I've been at CSIRO. So I think that was another motivation to change. And the idea of taking some time out from everything that I'd spent, I guess, my 40s building, building a big research group, diversifying to lots of different areas, hiring lots of people, it got to be pretty big. And just to change gear, focus on one thing, to be a couple again, right? Just the two of us in an apartment in Paris, that's pretty nice. Kids were sufficiently grown up that we left them behind. They did come to visit, but it was just us, and I could single-mindedly focus on that one particular task. It was a very idyllic few months, but enormously productive. And then after that, spent 3 months at Oxford with Paul Newman. He was my host. Paul I'd met a long time ago. He'd spent some time at University of Sydney. Our paths have crossed many times. So he hosted me, spent 3 months there writing some more book. And it's been quite a successful book, in part because it's got a particular perspective of someone who's actually been doing robotics for a long time. So it incorporates the bits of robotics that are actually useful in practice and just enough theory to get you by. So it doesn't kill you with theory, but it's the theory that I thought was sufficient to do robotics. It was also a very hands-on book, so it made use of this robotics toolbox that I'd already written. So I had the toolbox. The book exploited the toolbox, so people could open the book and there'd be lines of code in the book, and if they wanted, they could type those lines into their own computer and duplicate the results that I had, or they could, then modify that, hack it a little bit, and apply it to something else. So it was the mode of expression of the book was text, pretty traditional for a book, and equations and code. So there are actually lots of lines of code all through the book. But to me, as somebody who really likes coding, that's what makes it real. It's not just an equation, here's some code that actually does a thing.
What we wanted to do next in robotics is, put the laser on a more randomly moving, I guess, sort of platform like a robot. The core team was a guy called Rob Zlot and Mike Bosser. And I remember Mike coming into my office one day and he had one of these laser scanners in his hand and he said, look what we can do. And he sort of just moved it around in his hand and out of the computer popped a beautiful 3D map of the room, from a seemingly randomly moving laser. And they kind of solved this key problem. And that then further developed into a proper handheld version, which was this device called Zebedee. And so this was a laser on a spring. So rather than have everyone just hold this thing and randomly move it around, they put a small laser on top of a spring, made a handle, and they would kind of walk around and it would bob up and down. And it was called Zebedee because there was a TV character called Zebedee who was a creature with, instead of having legs, he had a spring. So we started mapping buildings, which seemed like a really good thing, and we got beautiful data out of that. And then I can't exactly remember how we ended up at the Leaning Tower of Pisa, but it was someone thought of this idea that we knew that no one had mapped the inside of the Leaning Tower of Pisa. Everyone had mapped the outside of the Leaning Tower of Pisa. And through all the various contacts, we somehow managed to convince the people that own the Leaning Tower of Pisa to let us go in before it opened in the morning. We got the hour before the standard public opening towers. They gave us the key. We spent that hour that morning walking up and down the stairs, and we managed to map this spiral staircase in the Leaning Tower of Pisa. And then we merged that with all the data that had already been collected of the outside of the Leaning Tower of Pisa. And then off to the side, CSIRO started developing a flying version of similar kind of laser scanning technology. So not the handheld stuff, but we had this dream, again from the movies. There was one day we all went as a lab to see this movie called Prometheus. And in that movie, they find the crashed alien spaceship, and someone throws this thing in the air, and it flies around autonomously and maps the spaceship. And some of my colleagues said, "Oh yeah, we could develop that," and they did. And now there's a product called HoverMap, made by a spin-off company of CSIRO called Emerson, and it does exactly that. You can put it in a mine and it can autonomously fly around with no prior map, and it will map the 3D structure and navigate itself just like the thing in the Prometheus movie.
So this is the HoverMap payload that we manufacture. This bit out the front here is the LiDAR. So this is a Velodyne LiDAR, which is usually used in autonomous cars. So usually this would be mounted to a vehicle. Inside there are 16 lasers which are spinning around, taking sort of measurements in the world up to 100 meters away. 300,000 laser pulses being shot out every second, and that's giving you a couple of slices through the world. On a drone, when it's flying, it needs to see up and down, not just sort of forwards and backwards. So what we do is we actually rotate this whole mechanism, and that gives us a full spherical field of view. So HoverMap basically is the LiDAR. We've got a computer on board, some other custom electronics, and the sort of the secret sauce is really our software, which runs on board here. And that does two things. It's collecting all this LiDAR data to produce a map. So after the flight, we process that using the SLAM algorithms to produce a map, but we're also using the same LiDAR data as the drone's flying to keep the drone safe. So when it's on a drone, it just basically clicks into the drone. We connect power and the signal to the drone, and then it basically becomes the brains and the eyes for the drone, allowing the drone to fly autonomously in areas where there's no GPS or a lot of obstacles. And as it's flying, it's using this LiDAR data to build an obstacle map around the drone so it knows where they are, and also figuring out how it's moving relative to the environment without using GPS. So that's the sort of the key enablers from HoverMap: flying where there's no GPS and avoiding obstacles. When you're operating, it's streaming the map to the operator on a tablet, and as you see this map appearing in 3D in real time, you can just tap on the map and tell it where to go, and it will then self-navigate to reach anywhere in that map or beyond the map that it's currently seen to.
So one day when I was driving to work, I got a phone call out of the blue from somebody I knew at QUT asking me if I'd be interested in a job there as a professor. And that sounded a bit interesting. And so I interviewed and they offered me a position. This is the end of 2008. And so I accepted, but I put some conditions on it, which is a little cheeky. One of the conditions was that a good friend of mine, Gordon Wyeth, who then was at University of Queensland, that they should appoint him as well, because A, he'd be a really good professor, and B, he'd been at New University. And I'd spent almost my entire career within CSIRO, which is a very different kind of beast. And so I thought that if I came to QUT knowing nothing about universities, I may not thrive. And so I thought, Gordon, he was looking for a change. He'd be a really good addition. And then there'd be two of us at QUT, and we could do awesome things.
So on the 4th of January 2010, we showed up for our first day at QUT. I had two of my students come over as well, and it was the four of us in January 2010. getting robotics started at QUT. And I remember in that first month, the four of us went and had lunch together, sitting in the botanical gardens. And we sat in the shade of a palm tree, right, skinny little tree, little tufty top, small patch of shade. And the four of us are sitting there. And Peter looked down the hill, and there's a big fig tree that had just spread out everywhere. And he said, right, 5 years' time, we're going to need that tree to get the shade for our group. Hey, we got there, we absolutely got there. But I still distinctly remember that lunch.
The environment's changed, so now I'm at a university, and universities do different things to what CSIRO does. And so, we need to put in place courses to teach undergraduates. We need to get research students, PhD students to push the research forward, because that's the way research is done at a university. We need to win grants, to bring in money to help fund the PhD students and the postdoctoral fellows and so on. And we needed a lab, a place where we could put robots. We needed money to buy robots. So there was a big program of work that we needed to embark on. So we did all those things. We put new courses in place, which we started teaching from 2011. We also went acquiring people, and so we brought people across, mostly from University of Queensland. So we brought Michael Milford across, a young researcher. We brought across Ben Upcroft, a lecturer at University of Queensland. He joined us. We brought across a bunch of PhD students, Gordon's PhD students from UQ. We brought them across to QUT.
I've been doing various postdoc roles for a few years, and then suddenly, out of the blue seemingly, I found out that Peter and Gordon had been in effect headhunted to QUT. And 2010 is a long time ago in terms of robotics in Australia, and so if you take those two people and put them at one university, you really create this critical mass. We referred to it jokingly as the black hole, which all the roboticists got sucked into. And so it was pretty much inevitable that we followed them over there and ended up at QUT and really never looked back. One of the things that we did a lot of was combining the biologically inspired mapping and navigation approaches that we were developing for robotics with some of the more formal, rigorous techniques that Peter brought to the table. And it was really interesting working at that intersection between, I guess, what you'd call classical robotics and these biologically inspired techniques. And it was a really interesting time to be in the lab.
So first started teaching robotics at QUT in 2011. 2012 was the second year of teaching. And from my previous experience with teaching, I thought, the second year is going to be the easier one, right? I did all the hard work the year before. A week before teaching was supposed to start, I fell off my push bike on the way to work. This was a misguided attempt to get fit. So I broke my kneecap. It was a very painful thing to do, and was laid up at home for 6 weeks on crutches. I couldn't come to work. So what I did was to narrate my lectures from home, and then I'd upload those to QUT, and Michael Milford played the lectures with the narration to the class, and graciously took questions.
So I remember the experience of having Peter painfully trying to remote in using relatively primitive internet back then and deliver lectures remotely.
Welcome to the third lecture in the image processing part of ENB 339. I'm Peter Corke, and I apologise in advance for any extraneous noise. The guy across the road seems to be doing building today. Don't know why. Okay, let's recap what we talked about in the last lecture.
And I think that was part of the stimulus for Peter recording some really high quality lectures and tutorials on robotics. And that's really where the amazing work that he's done now that has led to the Robot Academy and many other great educational projects really had its origins in Peter falling off his bike.
And at the end of the semester, when I was up and about again, I uploaded them to YouTube, which was a thing by then. And there were bits of educational material on YouTube as well as the entertaining. And there it sat. And then sometime later, maybe a year or two later, I noticed that there were a lot of downloads and views of these lectures, and people wrote comments, and they wrote nice comments about the lectures, which were, put together in a bit of a hurry, and the soundtrack was far from perfect. Anyway, people really appreciated it, and they appreciated the way that I structured the material. It was fairly accessible, not just enough theory and no more. That's the principle. In this lecture, we're going to learn about how we get a digital image into a computer. For robotic vision, this is the essential first step. We have to have the visual information inside the computer so that we can manipulate it and eventually extract meaning from it. So this is the essential first step. Digital images today are I thought, well, okay, I have these videos which people found interesting. Maybe I could, posh it up and produce MOOCs. And so convinced QUT that this would be a good thing to do. QUT had never done these before. Assembled an awesome team of people, 20 people or something, to put these together. It was a solid year's effort, not just myself, but all these other brilliant people, learning designers and graphic designers, project managers, fantastic team. And so we created these MOOCs. We put them up and we ran them. First one got 10,000 people enrolled, which is very, very gratifying. And we ran it for about 2 years. We ran these MOOCs.
Peter delivers fantastic lectures and has really great material that he spends a lot of time just getting it right and thinking about how to communicate it. I think the other thing is that people are hungry for this information. We've seen in the last maybe 6 or more years this movement of massive online courses and the ability for anybody around the world to sign up to courses and to train themselves up in these areas. It's this whole idea of democratization of education, and so I think it fits really nicely into that model. And then also having the quality material means that he's built up a good reputation for that course. Yeah.
So what we did is took all of the content that we developed for the MOOCs. So the MOOC comprised about 200 lessons. Each one's a 5-minute video, roughly. If we put it all online, it could be viewed either as a linear narrative or it could be random, like a Wikipedia. It's 200 articles about robotics, and you can just search them out, or you can watch them in a prescribed order. So that's what the Robot Academy is. It's a website that contains all the things we created for the MOOC, but accessible randomly or in order. And that has been phenomenally successful. So I think now it's something like 1.5 million lessons have been delivered. Every minute, somebody watches a lesson. And these are from all around the world. Let's imagine we have a robot and we want to position its gripper with respect to this purple triangle. Imagine that we want to have the gripper directly above the center of the triangle and at a height something like this. So if we had a camera on the robot's gripper, it would see a view something like this. In the particular view that the robot is seeing from here, the pose of the gripper with respect to the object is implicit. For instance, if the robot gripper was initially in a position like this, we can see that the image acquired by the camera is quite different. So if we could come up with a control algorithm that would change the view from this to this, then implicitly the robot is going to perform the desired motion in the world coordinate frame. Sometime 2012, 2013, a mate of mine at ANU, Rob Marnie, I've known Rob for a long, long time. Rob's a mathematician. He plays in robots and vision. So we got many common interests, many common friends actually. And so he had heard that there was an upcoming round for Centres of Excellence to be funded in Australia, and this round comes up every 3 years. So Rob told me about it and said maybe we should put in an application, a proposal for a Centre of Excellence.
It was really formed around robotic vision, so that the intention of the Centre of Excellence was to create a field, robotic vision, which didn't exist before. So there was no field of robotic vision prior to 2014.
So it seemed like a good idea, but to get a Centre of Excellence, you need to have a lot of high caliber researchers. It can't just be Rob and me, that wouldn't work. And so a couple of things that had changed lately in the Australian landscape. So one is Ian Reid, who's an Aussie who'd spent a long time at Oxford, had chosen to come back to Australia somewhat recently at that point, and he landed up at the University of Adelaide.
And I got invited to Kialoa, where we hold RVSS every year, for a NICTA summit, and I was giving a talk there, and Peter Corke and Rob Marnie were also there, and they had already started a conversation about maybe we should try to do something, and the fact that I was there, and about a year before I arrived, Tom Drummond from Monash had also come from the UK back to Australia. And we realised during that retreat at Kialoa that we had that critical mass of people working in robotics and people working in computer vision, where we could say we have world leaders in these areas, and we can try to bring these fields back together again.
You know, Rob had a lot of the control expertise. Tom, fantastic in machine learning. Ian Reid, amazing computer vision person, all tied together, you know, with Peter and his knowledge of robotics. And so it was kind of that dream team with a dream problem at that time that was very easy to relate to the Research Council to say, here is an opportunity to make some fantastic advances for Australia, and to show that we had the right people at the right time for the right problem.
The centre started at the beginning of 2014. I was the director, and one of the first jobs was to appoint a chief operating officer, and we were very fortunate to recruit Sue Kay into that role, and she was very formative in standing the centre up, putting in place all sorts of processes and procedures, helping us to clarify our thoughts, help to clarify the messages that we sent, and generally sort of portray ourselves to the outside world.
So the vision for the Australian Centre for Robotic Vision was really about pulling two different disciplines together, robotics and computer vision. There are only a few people in the world, and Peter Corke is the most notable of them, who have always combined those two areas. For most other people, they've mainly been in one camp or the other. And Peter could see that this was something that was really holding robotics back. Peter's contribution was really to make that first step and combine the communities and get some common understanding of the values of each community. And certainly I think that robotic vision is now an established field. It is very common in the robotics community for people to apply computer vision to what they're doing.
Immensely proud to be here tonight. It's been a fantastic night to see so many friends who've been engaged in making the centre a success, and I couldn't be more proud and happier to be here at the launch of the ACRV.
So this is all from the ACRV launch here at QUT.
A big challenge within the centre was to bring people who identify themselves as roboticists and people who identify themselves as computer vision people, because we were trying to create robotic vision people, and they didn't exist in the world. So we had to get people to kind of leave the community that they thought they belonged to, and to consider themselves part of this new community of robotic vision people. And there's all sorts of things we can do to try and encourage that sort of thinking. But one of the things we did that I think was very important was to enter a competition. And this was a competition run by Amazon.
The Amazon Robotics Challenge was a challenge run by Amazon in 2017. And it is a competition in the order fulfillment space. So can a robotic system help in an e-commerce setting and pick up orders out of a box and stick them into a cardboard box that you get home shipped to you? So we competed about 15 other companies and research institutes. So some of them were industry players like Mitsubishi and Panasonic, but also really well-known, established international research universities, MIT, Princeton, University of Bonn in Germany. So that was sort of a wide range of competitors, some of them building their own robotic system, and other ones partnering with robotics providers. In the Amazon Challenge, we used our own robotic system called Cartman. That stemmed from some of the research that we'd done prior to that Amazon Challenge, but also our first experience in the Amazon Picking Challenge, which was in 2016. Then we used a custom off-the-shelf robotic system, the Baxter robot, and we saw that certain capabilities of that system were not well designed for that specific use case. So if you focus on a specific use case, you can usually optimize the robotic system for that specific problem. And that's how we brainstormed ideas of how we can optimize a system that actually is really good at picking out of a box. And that's how we came up with Cartman. That's how we came up with the idea of like a Cartesian robotic system. And it sort of progressed over the months prior to the challenge to something that was actually a useful and usable system.
To get a robot to pick something up and move it is incredibly hard for a robot. We just take it for granted how easy it is for us. We have great hands and great vision, and robots don't have that yet. So it's an extremely hard problem. So that's why they made the competition. Can we get robots to pick things up and move them?
The Cartman was an example of robotic vision, right? It's the fact that we had available to us. We weren't just treating the camera as a sensor, robotic sensor, right? We were treating the computer vision problem as a real computer vision problem, treating the robotics as a real robotics problem. So it sort of brought together the strengths of the centre in that way.
We had vision contributions from Adelaide. We had people contributing from Monash and from ANU. Partly it was that team effort. Partly it was the taking on the world and showing that the stuff that we were producing was as good as anything and better than anything. And also it was a really tangible result that we could go back, for instance, to the funding body, to the ARC, or to government and say, look, this is something that Australia is genuinely doing better than other people in the world.
As part of the challenge, we actually built physically the robot ourselves here in the lab, actually just across over there. As a part of that, actually involved on a week-by-week basis, and in the end, day-by-day basis, actually physically building stuff. That means like, going down to the workshop and cutting an aluminium extrusion in the right length, 3D printing parts, sticking them together, soldering stuff on top of PCB boards. So all that happened in more or less at the parallel to building the software system that did the visual understanding and the brains behind it.
Yuxi Leitner, who led the team for the 2 years that we played in the competition, he has now left to start his own robotics company called Lyro Robotics.
Lyro built the brain, the eyes and the hands for the next generation of smart robotic systems. Lyro Machine Intelligence is the brain that makes every robotic system smart. It makes a decision of what item to pick, it can pick any item and make a decision on how to place it. It learns with every item that is newly picked and gets better over time. The eyes of the robotic system is based on our state-of-the-art computer vision system. It learns what items to pick, how the item looks, and even detects the items if they're moving fast on a belt or are in an untidy box. The correct gripper makes all the difference. We design our own hands and integrate them even with off-the-shelf gripping systems. From fast to flexible, from soft fingers to suction cups.
In 2017, I won the award as the Australian University Teacher of the Year. It's an award that's made me enormously happy. I think the reason for that is, for most of my career, my self-image has been as a researcher. I think my day job has been doing research. But I think I got this passion for teaching and education from my very first gig at Melbourne University through writing textbooks and so on. And I think what I'm really happiest about with the award is that it recognised the contribution to teaching, which is my secret passion, but not my day job. That was just wonderful. where they fit into society, why robots are important. Now, it's been, as I say, quite a journey. We've talked about the history of robots, mankind's fascination with building things in the image of living organisms. And I think what it did is it recognised a big body of work, contributions to teaching. The one is this robotics toolbox software, which is a tool that people can use for teaching. Students can use it, lecturers can use it. The book uses the Toolbox software to explain robotics concepts. So I've got the tool and I've got a book which explains it. And then on top of that, it's the Robot Academy, which uses the book and the software to explain things in my own voice to students. So it's me talking to the students. And so it's this progression, it's these layers of tools, which together I think is very, very effective and widely accessible for educating students about robotics. They have the different types of joints that they have, and then work on the mathematical description, the mathematical relationship between the joint angles and the robot end effector pose. The robotics toolbox software uses a computer programming language called MATLAB. And MATLAB's a proprietary language created by a company called the MathWorks, who are based in Boston. And I've been using their software since I think the company was created in like 1984. So I've used it for my whole life. I find it very productive. And I've had good relationship with the company over the years. 2018, I took a sabbatical and chose to spend it in Boston and spend a fair bit of time at the MathWorks headquarters. So for me, as somebody who'd been using this software for most of my professional life, here I was going to the mothership, all right? And it was wonderful. Fantastic people, they were very welcoming. They asked my advice about all manner of things. I got to be a guinea pig tester of upcoming features of the software. I got to meet the founders. You know, it was a great experience. The big challenges for robots is still the ability to understand what's going on around them, right? So we've done a lot of work using vision to understand what's going on in the world around the robot. It's the sensor that we use most to understand what's going on in the world around us. And it's always been my belief that that's sufficient. The information that we get received through our eyes is enough for us to be able to do all of the important tasks. We can drive a car, we can write a book, we can pick fruit, make a meal, mostly using information that comes to us from vision. So I guess I've been a big believer that that's enough for a robot to be able to do what it needs to do. All of us have grown up on a diet of fiction about robots, portray robots that are very, very capable. And the things we are able to create today are pale shadows of what robots should be and could be. There are also challenges for robots that my 10-year-old self would not have twigged to. And these are sort of ethical and societal challenges that robots bring. So problems around robots and jobs, it's talked about a lot. I think my views on that are changing over time. Robots and information privacy, robots and cyber hacking, robots and warfare. These are big challenges that I think as a robotics research community we don't focus on enough. Too many of us have just got our heads down working on the tech and not thinking about the big picture issue. It's not something we discuss at robotics conferences, which is disappointing. So the whole journey has really been quite accidental. It's just a series of decisions that seemed like a good idea at the time. It's been a wonderful path through life and through technology, but no plan.
you.